Okay, so let's get started. So today's recitation is on virtual memory. So we're sort of between two labs here. Your shell lab is due tomorrow, 11:59 p.m. as normal. And then Malak lab will come out tomorrow. But Malak lab is a longer lab. You get a couple weeks to do it. And so we're not going to talk about it much today. We're going to talk about Malak lab more next week and 2 weeks from now. But today we're going to talk about virtual memory instead in the meantime. So a couple things about Malak lab, though. We're going to talk about Malak lab and shell lab briefly before we get to virtual memory. Malak lab will then be due November 19th once it's out tomorrow. But even though that's a lot of time, you should start early because it is traditionally the longest, most involved lab for the course. As long as you start early, it shouldn't be too bad. But you will want to spend a significant amount of time designing it so that you don't make a mess of everything once you go to implement it. And you will probably need to do at least a little bit of debugging. And the debugging can be tricky because you've got a lot of low-level stuff going on. So a couple things about shell lab based on what we've heard. So one of the things about the traces, in case you haven't noticed, is the way the traces work is they run echo to print out what it's about to actually run during the trace file. So if you are seeing echo in your job list when you run a trace, what that means is that you didn't remove it properly because the echo is a foreground process and it should go away before it actually runs the real process. So if you're seeing something with echo there, the reason that it's there is because that's how the trace file works. Is the reason why it got put there, and the reason why it's still there is because there's something wrong with your removal on your job list. So make sure you're actually opening the trace file to see exactly what it does if you're confused about what's going on. Sig suspend. So sig suspend, maybe a lot of you have found is helpful for this lab. If you have not realized that yet, I will tell you now, sig suspend is helpful for this lab. So you might have noticed that there's sort of two places where you want to be able to use wait PID because you have to handle these background jobs, and you also have to be handling a foreground job, and maybe a background job is going to stop while your foreground job is running, and you don't know what order these things are going to happen in. But you can't have wait PIDs in both places because each wait PID just sort of gets whatever children happen to be terminating. And so you might have said, well, I'll just use wait PID for the background jobs, and then just to make the foreground process not do anything, I'll just sort of sit there and I'll sleep, or I'll just have a while loop that just waits. And that's a bad idea. You could either you'll be wasting a lot of CPU power, or you'll be introducing race conditions, or both if you do that. And those are undesirable, so you should look into how you can use sig suspend, because with sig suspend you can sort of get your process to just only check and see what's happened every time a new signal arrives, and you do get a signal when children die, so that's good. And you can sort of just every time a signal arrives, you check and see if there's something you need to do to end the foreground job being blocked, and if not, you can just go back and sig suspend again. So you should think about how exactly to implement that if you haven't gotten that already. There's some details about how sig suspend works there. You can also read the man page. And then we even have a great example of it for you. And so these, this will be online and you can look at that in detail. Are there any questions about it from here? It's not too complicated. System calls and error handling. So you should always handle the errors from any system call that you might be making. So anytime, if it's a fork, if it's an exec, if it's an open, a file, whatever it is, you should be prepared for the fact that maybe there will be an error in that system call, and you should be doing something reasonable to handle it if that occurs. So the reasonable thing, it's different depending on what it is. For some things, maybe the reasonable thing to do is to just print out an error message, but your shell keeps going. So for instance, maybe I try to exec a process that doesn't exist because the user typed in something bad on the command line. Well, you shouldn't just shut down the host shell because of that. it would be much better to handle that error by printing out an error message, but keep going. Yes?
For the ones where we're given wrappers
Mm-hmm.
with the capital letters, we don't need to handle errors for that, or should we?
So, okay, yeah, so we've got wrappers for you, and what these wrappers do is they handle errors by exiting. In some cases, that's what you want. In other cases, that might not be what you want. These wrappers will be too aggressive about just terminating the program in some cases where you could have kept going. And so you should think about, in any particular case, if the correct behavior is to terminate the process, if this is something that, well, we can't recover from it, or if there's a way that we can keep going. And you can, of course, modify a copy of the wrapper to do something else that you want if you sort of just want to have the wrapper function there but have different error handling behavior inside it. Okay. And of course, many of you have seen from Cache Lab that yes, we do take off style points for things. This is one of the things that we would take style points off if you didn't handle these errors, so make sure you do that.
What's the difference between the app error that's given to us and the Unix error? Like when do you call it?
The app error?
There are two functions that are given to you in the handout file for shell app. There's a function called app error, and then there's one called Unix error.
App error. Not APP app?
No, like just like app. Yeah, APP. Like how else do you spell it?
I'm not sure what that function is for. The Unix error one is part of the CSAPP wrappers. That's what they use to just print out the error message and then exit. I'm not sure what the APP error does that would be different. I don't have a copy of the handout downloaded. Okay, let's see. I/O basics. Okay, so one of the things about Shell Lab that we did not talk about last week was I/O. So the very end of Shell Lab, you're doing a bit of I/O redirection. It's like the last two traces, if you haven't gotten there yet. So some things about I/O. There's sort of 4 basic operations. So we've got these files, and what do we do with them? Well, we can open files, we can close files, we can read bytes out of a file, and we can write bytes to a file. And then the way that we reference these files from our program is that we have file descriptors. So when you do an open, you get back a file descriptor to the file that you opened, and it's some positive integer, or a negative one in the case of the errors, the error code. And so what happens is you start with 3 file descriptors. Every program starts by default with 3 file descriptors, and 0 is standard in. So that's the things you type into your terminal going into the program. 1 is standard out, so that's the stuff being printed out to your terminal, and 2 is standard error, which is a separate output stream, so that you can redirect it separately from standard out, which is typically used for error messages and stuff. So the way it looks is every process gets a file descriptor table. So this is all of your file descriptors, which are just these integers mapping to an open file table. So you've got a table of all of the open files, and it's shared by all of the processes. And what that does is it keeps track of where in the file you are and how many file descriptors are pointing to it. So that position sort of is, when you do a read on a file, you want to be able to read some number of bytes, and then the next read you do should be the byte that comes after what you just read. It shouldn't start again at the beginning. And so it keeps track of where it is in the file with the position, and then it keeps track of how many file descriptors are pointing to it, because once there's no more file descriptors pointing to it, we can close it. And then those just point to actual information that's pertaining to the real file on the disk. So stuff like its size, what type of file it is. And the details of that aren't important for Shell Lab, that right-hand side. But if you want to know more about that, that's in the textbook. It's sort of the descriptor table and the open file table that we care about here for Shell Lab, because we're going to be manipulating the descriptor table and sort of the arrows between them. So in this example, we've got our standard out is pointing to file A, which we say is the terminal, which is what it points to when you open it up by default. And then we've opened up some other file. We opened up one that's a file on disk. and it has file descriptor 4. So we can have multiple files in the file table pointing to the same file on disk. So this is what happens if you just open the same file twice. So on the disk, it's actually the same file. If if you're writing to it, then both copies know that you're writing to it. You can see those changes across both, but you can be reading independently with 2 independent positions through this same file just by opening it twice. And then, yeah, question?
Shouldn't the reference count be 2?
Reference count be 2. So we've got 2 different files, and each has 1 file descriptor pointing to it. So it's 2 different entries in the file table, but both point to the same file on disk.
Okay.
And so what this means is that they can keep separate positions in reference counts, but ultimately they are referring to the same bytes on disk. So one of the questions is, okay, what happens when we fork? So we have a process, and it's got a couple open files here. File A and B are open, pointing to some things on disk. And we're going to do fork, so what happens? So the descriptor table is 1 per process. So obviously we're going to have to get a new descriptor table because we got a new process through the fork. But what does it point to? It's all going to point to the same entries in the file table that the parent did. Both the parent and the child have the same thing, so we get an extra reference count on all of those. And it's at the same position that the parent was at when it did the fork. But they're still the same, it's still only 2 files on disk. We're not copying and pasting files on disk by doing a fork. That would be a resource nightmare. Make it very easy to use up a lot of disk space. So, okay, so any questions about that? You've sort of just duplicated all of these arrows on this side over here. Okay, and so then the part that you're actually doing, so you'll do a fork, you do fork, and sometimes this happens, so you need to know what this picture looks like. But what you actually need to implement for the last couple of traces is I/O redirection. We ask you to be able to handle the caret, not caret, the sort of greater than and less than symbols, which do I/O redirection so that you can output to something other than the terminal or take input from a file. And so the function you'll want to use to do that is a function called dup2. So dup2 is after dup and before dup3. Neither of those are as useful as dup2. Dup2, what it does is it takes 2 file descriptors, an old file descriptor and a new file descriptor, and it takes the entry for old file descriptor and it sets it to be equal to the entry for new file descriptor, which I personally think is kind of backwards because you end up with 2 copies of old file descriptor and no copies of new file descriptor. But that's the way it's named, and if you look at all of the man pages, they're going to have the same old and then new. So what happened is we gave it 4.1. So 4 is our old file descriptor and 1 is our new file descriptor. And after the dup2, what happens is both file descriptors are pointing to the same file. So what this is doing is it's taking that arrow in the file descriptor table. So we have this arrow, 4 is pointing to B and 1 is pointing to A. And now we're going to do a dup2. And what happens is now 1 is also pointing to B. So we're just taking that arrow from the file descriptor table and sending it equal to the other arrow. It's sort of like a pointer aliasing thing that we're doing here. And then, of course, the ref counts change. So because it's the old file, the old file gets an increment on its reference count because it's got another arrow pointing to it now, and then the other one gets its reference count decremented, and so in this case this actually becomes 0, so it can be closed. If there were other arrows still pointing to it, it would remain open with whatever reference count it had before the dup2, but decremented by 1. And so now we have 2 different file descriptors, and if we write to either of these, it's going to write to the same file B. And so this will be useful for you to make your shells write to or read from files other than standard in and standard out. Any questions about that? Yeah?
For the case where you fork the child and
Mm-hmm.
What are there possible aliasing bugs you get with that?
Possible aliasing bugs. So what are you worried might alias?
Like if the child does something that you don't want is that reflected in the parent?
Yeah. So they have the same file table with the same position in it and stuff. So if we're reading from one, it's changing this position that the other is going to see. So if we read from the child and then read from the parent, we can get, we won't get like byte A. If the first byte is byte A, we don't get it twice. We get byte A and then whatever comes after it. Yeah. So you do have to watch out for that if that's something that might be bad. Any other questions? Okay. So a quick sneak preview of malloc lab before we move on to virtual memory. So malloc lab, you're going to be writing your own storage allocator. So you're going to be implementing malloc, free, realloc, and calloc. So those are sort of the four main functions for memory allocation. And so in class, you're going to be learning about different ways to keep track of free and allocated blocks. So the purpose of the memory allocators, so these are the ways you get heap allocated memory. And the heap is just this huge chunk of memory that can be shared by all different parts of your program. And you need some way of keeping track of which bytes are being used by the program and which bytes you're allowed to give back when someone asks for more bytes with a malloc or a calloc. And so, the way a user asks for more bytes is they do malloc or they do calloc, and the way they say I'm done with these bytes is they do free. But your memory allocator needs to keep track of, well, when I do a free, how many bytes were allocated that address that I'm now allowed to use for whatever else, and stuff like that. So you need to sort of keep track of what memory is free and what memory is allocated so that when these different function calls come in, you can give back memory appropriately. So there's a couple different ways of keeping track of these. They're called like implicit linked list, explicit linked list, segregated lists of different sizes. So sort of it's different ways of prioritizing, well, what do we want to do quickly? Do we want to be able to quickly find free blocks? Do we want to be able to quickly, do you want to be efficient in how much memory we're actually using? Because, the thing is, if I say, say I've got the memory is just a big long sequence of bytes. If someone asks for some bytes and I say, okay, here you can have these bytes, these are in use now. And then they ask for some more bytes and I say, okay, you can have these bytes, these are in use now. If someone asks for a chunk of memory that's bigger than this, we can't give them this. So it just remains empty. And so one of the things we are concerned about is, given an arbitrary sequence of allocations and frees, how do we make sure that we minimize the amount of unused space at the end of the run? Because this is sort of space that, well, we can't use it for anything unless someone asks for an amount this small. It's effectively wasted if we never are able to allocate it. So that's one of the things you're dealing with. You're dealing with, can I get back memory quickly, and can I get back memory in a way that overall I've efficiently used the memory and haven't left a bunch of empty space on the heap that's not allocated for anything. And so, you're going to make a bunch of different design decisions about how you're going to look for free chunks of memory, the linked list that you're using to keep track of this. Do you want them to just be singly or doubly linked? And stuff like coalescing. So sort of if there's another thing, so I have a chunk of memory and I've got some allocated bits, and say this gets freed and then this one gets freed. Now I actually have this much free space. So at some point it would be nice to go along and say this isn't two small blocks, this is one big block because they're right next to each other. And so you'll have to be able to think about things like that and make design decisions about when and how all of that's going to happen. So pay attention in class because the stuff that's talked about in class will be very useful. Then here's another thing about version control. So if you're familiar with version control, it might be helpful for malloc lab. If you're not familiar with version control, I wouldn't recommend trying to learn it while doing malloc lab. I would instead recommend just copying and pasting your file every now and then, or submitting to Autolab so that you have backup copies of the different versions in case you totally mess something up and want to just say, I want to undo my last several hours of work. It happens sometimes. Or maybe you don't want to undo it, but you just want to refer back to what it was because you changed something and you forgot how it was before, and you knew that whatever you did was wrong, and you want to see what it was before without you doing it. Okay, so now we're going to talk about virtual memory. So there really isn't a lab on virtual memory, since this is sort of between Shell Lab and Malloc Lab. But this is something that might be and really probably will be on your final exam. So it's still something you need to know. And is also useful in terms of understanding how computers work. So far, we've been talking about memory, and we just say, we've got this flat array of addresses, and the stack starts somewhere, and there's a heap somewhere, and there's all this other stuff on it. But we're also running multiple processes at one time, and you saw that in your Shell Lab. You've got a ton of processes, running all at the same time, even just that have been forked off by your shell. In addition to the other ones running on the system. And you might open them up in GDB and notice that they're reading and writing to addresses that are the same. And so the question is, well, how does that work? Because they can't possibly be reading and writing to the actual same addresses, otherwise they'd be constantly corrupting each other and everything would crash as soon as you opened a second process. And so the answer is, those aren't the actual addresses that they're reading and writing to. There's a secret layer in between the process and the actual hardware, where the process is writing to virtual addresses, and then the hardware is actually turning those into real addresses in your RAM that are distinct and disjoint so that nothing conflicts with each other. So the question is, how does it do this? Because that sounds pretty fancy. So you have your program, and it's got all of its virtual addresses, the ones that the program sees that it gets to use. And then you've got some physical address space. And it actually turns out that the physical address space tends to be smaller than the virtual address space. And this isn't too surprising because the physical address space is actual bytes that are addressable in your computer in the actual hardware. And your computer probably has somewhere around 8 gigabytes of RAM, plus or minus, a factor of 4. You've probably got somewhere between 2 and 32 gigabytes on any computer you have. And so, that's a lot, but it's not nearly as much as can be addressed with, 64 bits. And so, there's this physical space. It's actually smaller than the virtual space. Current virtual addresses don't even use the full 64 bits because that's just way more than you ever need. But it's still more than what you get physically. And so what has to happen is the virtual addresses that are used need to map to real physical addresses. And so sort of what we have here in this diagram is we're saying, well, we've got some virtual addresses up here, and it's going to map to this physical address, and this one to this one, and this one to this one. And then over here, these red ones, there's other processes, and they also get distinct physical addresses that this process doesn't get to use. They can't share anything. And over here, we actually even see that this virtual address maps down to this physical address, which is in a totally different order than the virtual addresses are. Sort of these guys are below it in the virtual address space, but above it in the physical address space. That's perfectly fine. The computer is just going to translate from virtual addresses to physical addresses in these chunks. And they don't need to maintain a particular order. They don't need to be contiguous. We can interleave the physical spaces of the different processes, and that's fine. So this diagram makes sense, what we're doing here. Yeah?
So if there can be more virtual space than physical space, does that mean then some of the virtual spaces pointing to the same address in the physical space, or how is that possible?
So it means that some of the virtual space is not going to actually point to anything in the physical space. So we haven't used the whole virtual space here. There's big empty chunks. And these aren't going to map to any real memory. And hopefully we're not going to actually try to put anything in them, so it'll be okay that they don't map to memory. If eventually we use more virtual space than we have physical space available, our computer's going to complain, and it's either going to crash or just like refuse to run the program or do something because it literally doesn't have any more memory left.
So what's the point of having more virtual space if you can never use actually more of it? Or is it where sometimes you like fill the virtual address space, but then it doesn't point to...
So there's a couple useful things about having the big virtual space even with the small physical space. One is that we want to be able to just compile our programs and not care about how much RAM is going to be on the computer that they're going to run on. So, theoretically, we could quadruple our physical space just by adding more RAM. And it would be nice if, we had a mapping like this where nothing about the mapping had to change in terms of like recompiling the program to now be able to use more addresses. So that's one reason. Another reason to keep these sort of separate concepts is that we want all of the processes to not be able to touch each other's memory. But theoretically, any one process could be using like most or all of the memory, depending on how many are running at a time. We don't know how much of the memory each process is going to be allowed to have. So we want to sort of allow it to have, as much as is possible. And then only in the cases where we actually don't have physical memory to support more things, deal with saying this is bad, rather than constricting it in the virtual case and saying that we're not going to allow you to write a program that might use more memory than is allowed. Yeah?
Can some addresses in the virtual space when mapped point to something on the disk?
Point to something on the disk?
Yeah.
So these will all point to things on in RAM, is what they do.
Not on the disk.
Yeah, not on the disk. Now, there's different mechanisms. There's a thing called a page file. These are all called pages of memory. And there's a mechanism called page files where what you can actually do is reserve a chunk of disk space that ends up being like extra RAM. And it sort of just swaps between RAM and this file on disk to treat it as this extra chunk of memory that it can keep stuff in. That's really slow because of the fact that disk reads and writes are really slow. But in a way, it makes it almost as if you're pointing to things on disk, although it will load them up into RAM before it can actually use them every time. Does that make sense? Yeah. Okay. Any other questions about this picture before we move on? Okay. So here's a different picture of it. So we've got these virtual pages. They're pointing to physical pages. We can actually, in the case of read-only, code like a library function. So maybe we have our code for printf or malloc or something. And everyone shares this, and you can only read it. You can't write to it. So in those cases, we can actually have a couple different virtual pages pointing to the same physical page, which is nice. We've actually reduced the amount of RAM we have to use. But for the most part, the pages are distinct. So let's see. So we need a couple different things. So we need a page table. So all of these, we block up memory into chunks. We don't want to do it one byte at a time. So we block it up into chunks, and those are called pages. So we can look up in a page table the translation from virtual addresses to physical addresses. So you give it a virtual address, and it's going to tell you, okay, this is the physical address that you need to go to get that. We're going to have something special called the translation look-aside buffer. So we'll get to the details of that later, but essentially it's a special cache to make these lookups to this table faster. And it's implemented the same way as the caches that we've seen before. And of course, we can sort of take this idea and just iterate it a bit. And instead of just having one translation from virtual to physical, we can sort of put several layers, and each layer does a little bit more, and then you sort of get a hierarchy where you can say all of these things are in chunk it up and say like all of these things are unmapped, and then you don't have to put them in your page table. It's sort of like it's almost like a bounding volume hierarchy. If you've done any computer graphics, it's sort of a way of describing a whole bunch of pages all at once in different levels of this. We'll look at a quick example of that at the end. So, okay, so how does this address translation actually work? So, we actually, we have a virtual address. How are we going to get into a physical address? So what we're going to say here is that we're going to have a virtual address space, and there's going to be n possible virtual addresses. So that means that each one is n bits long, right? N bits gives you 2 to the n, where n is, 2 to the n, lowercase n. Lowercase n bits gives you 2 to the n possible addresses. And similarly with the physical address space, there's going to be m physical addresses, so lowercase m is going to be the log of uppercase M, so that we get 2 to the m equals m, uppercase M. Okay, and then we're going to have pages with size p. So what that means is that the address offset is going to be lowercase p. And what the address offset is how far into the page we need to go to get a particular byte of memory. This is very similar to like how we had block offset and caches. If we had that number where we said, okay, we've got this chunk of memory, we've looked it up, how far into it do we have to go to get the one we're looking at? That's what this address offset is. We've got a page of memory, how far into it do we have to go to get the byte we actually want? And we're going to make these two the same. We're going to make the offset for virtual pages and physical pages the same, so that the translation between them is just the identity function. We just copy it over. We don't have to change it at all. That makes things faster. So, okay. So here's a diagram. Maybe a little bit confusing with all of these arrows, but here's what's happening. So we've got a virtual address that we want to look up. So we split it up. We've got the offset based on how big our pages are. The lower bits of it are going to be the offset. And the upper bits are going to index into a virtual page number. This is very much like how we had sort of a set index and a block offset in our caches. And so we've got our page table, which starts at some page table base register, which is just stored somewhere else for the process. And each entry in the page table is a combination of a valid bit and then the physical page number that this address, this virtual page, should actually go to. So we look up our virtual address. We're going to do a couple things. So if it happens that the valid bit is 0, then what that means is that we don't have the page in our memory right now. It's a page fault. And so we talked about faults last week. What we can do is we can go and handle this fault, and hopefully the kernel will be able to load up some memory and put it in our page table for us. And then it'll re-execute that instruction and try to get this memory again. And so that's what happens if the valid bit is 0. If the valid bit is 1, then we know that we actually have a physical page corresponding to this virtual address. And so, okay, so this page fault thing is, to continue the analogy with caches, is similar to when you do a cache miss and you have to go load something up. And now you can do it again and it'll work. So then we put in this virtual page number index into the table, say the valid bit is 1 now. It maps to a physical page number. So in order to actually construct our physical address, we just copy over the page offset, because we've said let's make them the same size so that they're always the same. And then we take the physical page number that we got based on the lookup from the virtual page number, and we smash them together, and now we've got a real physical address. And if we go there in RAM, we'll get the address that we were looking for. We'll get the bytes that we were requested to get by the program with its virtual address. So does that sort of make sense, what's going on here? Cut it in half, use the page number to look up a physical page number, and then put them together. If it fails, then the operating system handles loading up a new page for us. Okay, so here we have, an example. So we've got 14 bits for our virtual addresses, 12 for our physical, and we said the page size is 64 bytes. So what that means, 14 bits of virtual, 12 bits of physical, and then since we have 64 byte page sizes, that means we need 6 bits to index into them, because 2 to the 6 is 64. So our offsets are going to be 6 of these bits, and then the rest are for the page numbers. Okay, so here's an example. Yeah, so I just told you the answer to the first part. Pages are 64 bytes. How many bits is the offset? It's 6, because 2 to the 6 is 64. So 2 to the 6 equals 64, because what we know is that the number of bits, we had the page size is equal to 2 to the number of bits in the offset, was the formula from before. So this is 64, so that means lowercase p is 6. Okay, so here's an example that we're going to do. So we want to find 03D4, and we've been given this page table, and so we're going to first find out, the virtual page number and then the physical page number and then construct the actual address. Okay, so let's start with the virtual page numbers. So we've got bits 13, 12, 11, 10, 9, 8, 7, 6, 5. Okay, so what is our address? Our address is 03D4, so how do we fill in? And we've realized that this is the VPO and the VPN. Okay, so I want to fill in the bits of this address. What are the bits of this address? Let's go from low to high. What are the first 4 bits? We're doing a hex to binary conversion here. 0, 0, 1. What was the last one? 0. Okay. Okay, so this gives us 4. Yeah, this gives us 4, right? So 2 to the 2 is 4. Okay, and so what's the next byte? The next byte is D. So what's D? D is equal to, let's see, A is 10, B is 11, C is 12, D is 13. So we want to somehow get to 13. So what's that? That's, 8, 12, 13, right? 2 to the 3 plus 2 to the 4 plus another one. Okay, so the next byte is 3. So how do we get 3? I think someone knows. 3, what's 3? I have a byte, there's 4 bits in it. How do I get the number 3? 0, 0, 1, 1, okay. 0, 0, 1, 1. And then the last one is 0. How do I get 0? Hopefully you all know this. Yeah, just zeros, okay. Very good. So, okay, so now we have the bits corresponding to this address. So we determined before that there's 6 bits for the virtual page offset, and then the remainder are the virtual page number. So this is our virtual page number. So what number is this? In hex, because it looks like our table is indexed by hex. What is it? F? Okay, so this is 0xF. We've translated this part into 0xF hex, 0f. Okay, so what do we do? So we've got the virtual page number, right? That's what we just figured out here, virtual page number. Now we want the physical page number. So how do we get the physical page number? Yeah, we just look at the table. So the table says virtual page number is F. What is the physical page number? It's D. Okay, and look, the valid bit is 1. If it weren't 1, we wouldn't be able to use that entry, same as caches. But the valid bit is 1, so that means our physical page number is D. Okay, so what's D in binary? Let's write this out again. We get, let's see, 1, 2, 3, 4, 5. Okay, so D, we already figured out D. D was over here, right? 1, 1, 0, 1. And we've got 2, 6 of these. Okay, so what's our physical page offset then? It's the same, right. We just copy this over. They're the same size, and that makes it convenient because we can just copy it over. They're going to be the same offset because we're keeping these pages the same size. Okay, so now we just have to translate this back into hex. So what was that? That was a 4. We know that one. What's that? That looks like 1 plus 4 is like, what, 5? Am I doing that right? And then there's, is that it? 0x354? Yep. Okay. So what did we do? So we figured out that the page offset was 6 because we knew 64 bytes, so we just took the log. We filled out the bits here by doing hex to binary, which was quite the struggle. So maybe you should practice that. And then we just took this upper half and looked it up in the table to get the physical page number, and then we copied that down there, and now this becomes a new hex number, and that's our physical address. Yes?
What is the VPN, or how do you calculate the length of the first, or VPN plus VPO?
So VPN plus VPO we knew because what we said at the beginning was the addresses are 14 bits. So then it's just going to be VPN is the number of bits in the address minus the number of bits in the offset.
Okay, so we're usually given that, or is that the standard for 64?
You'll be given some numbers that correspond. You'll be given enough numbers that you can figure out the remaining ones. Yeah. The standard for 64 I think is 40 bits, but that would be a bit long. Yeah, so we're not going to do that. That's used right now by Intel machines as 40. I mean, ideally, in the future, they would scale all the way up to the full 64 because that's how many is supported. But right now, we don't need that much RAM, and so you might as well not spend time translating addresses that big. Yeah. Okay, so that's that one. Okay. So then there's the whole translation look-aside buffer thing. So right now, we just did this one, and we didn't have a translation look-aside buffer implemented. And what that means is that we're going to do twice the number of memory accesses that we have in our code. Because what we have to do is first we have to go to memory to get this page table and do this translation, and then we have to go to memory again to get the actual thing there. So, it would be nice if we could, when we're accessing addresses repeatedly, because we know, locality, we tend to do that. We tend to access the same addresses over and over. It would be great if we didn't have to go to memory to do this translation, especially if we've just done it. And so the solution to that is the translation look-aside buffer. So this is a special cache that is used by this memory mapping device in order to keep track of some of the information that it might be reusing over and over. So what we're going to do is we're going to take the VPN part, just the VPN part, not the whole thing. We don't care about the offset, that's just being copied over. We're going to take this, and this is going to become something that gets split up into an index and a tag and goes into a cache. So now we're going to repeat the cache recitation. So what do we have? So we said, okay, in this case, this is a new example. I don't know if I should. I guess I'm going to erase this one. I'll sort of leave the top of it up for now. What we're doing, so we're going to have 1 megabyte of virtual memory. We're going to have 256 kilobytes of physical memory, 4 kilobyte pages, and then our translation look-aside buffer has 8 entries and is two-way set associative. So now we've got a couple questions that we have to answer. You should be good at this sort of stuff because this is the sort of stuff they'll be expected to do efficiently on the final exam, for instance. So how many bits are needed to represent the virtual address space? Got 1 megabyte. 20. Okay, so we're going to say 20. So we want to do log base 2 of 2 to the 20 equals 20. Okay, cool. It works. Okay, and we have, so this is how many bits. I guess I'll label them 1, 2, 3, 4, 5, and 6. So that's part 1. How many bits are needed for the virtual address space? So we took 1 megabyte, that's 2 to the 20 bytes. How many bits do you need it? Take log base 2, you need 20. Okay, how many bits are needed to represent the physical address space? We've got 256 kilobytes. So what's 256 kilobytes? A kilobyte is 2 to the 10. So we're doing log 2 of 2 to the 10 times 256. That's what, 2 to the 8 times 2 to the 8 equals 18. Does that work out? That seems to work out because that's 2 less than this, and they're a factor of 4 different, so that seems believable. Okay, how many bits are needed to represent the offset? Someone else answered this one, so we've got 4 kilobyte page size. How many bits do we need to represent the offset? Okay. Yeah, so how did we get that? We want to take log base 2 of the page size. So what's the page size? It's, well, a kilobyte is 2 to the 10, and then 4 is 2 to the 2. So then the log base 2 of that is just 12. Okay, so 12 bits for the page size. Okay, now what do we know? We say that the translation look-aside buffer is 8 entries, two-way set associative. And we want to know how many bits are needed to represent the virtual page number, and then how many bits are in the TLB index and how many bits are in the tag. Okay, so part 4, how big is the virtual page number? We know that this is our virtual address space size. This is our physical address space size. This is our offset size, our page offset. So how many bits do we need to represent just the virtual page number part of our addresses? 8. Yeah, okay. So how did we get 8? So 8 bits. How did we get 8 from these numbers? I only see one reasonable way to combine these to get 8. We took the number of bits in our virtual address space and subtracted out the number of bits used for the offset. Because the virtual address space, the bits are just split into the page number and the offset. We've got the page number here, and we've got the offset here. So if we have 20 bits total, and this is 12 of them, then the remaining ones have 8. Okay, so we've got 8 bits for our virtual page number. And now we're going to use these 8 bits. So this, oh great, this happens to be 8. Okay, so we have 8 bits. And we want to use them as an index, as a entry that we're going to cache. So we're only using the virtual page number part of it. We don't care about the offset. So how do we know? So we want to know how many bits are in the index and how many bits are in the tag. And we know that it's 8 entries, two-way set associative. Okay, so the question is, how many sets are there total? Is the first question we're going to ask. How many sets are there in this cache? 16. So there's 8 lines and two-way associative. So 4 sets, right? So there's 4 sets and each one has 2 lines in it. Okay? So the index is used, the set index is used to get the set. How many bits do we need for the set index if we have 4 sets? 2, yeah, 2 bits. 2 bits for the set index. This is the TLB index. TLB index. And then how many bits do we need for the tag? What was the answer?
Just the rest.
Just the rest, yeah. So this is the same cache stuff we've used before. You know, you have your address that you're caching, and so you sort of have your set index, and you've got your tag. And in this case, we don't have a block offset because that's not what we're doing. So we've just got the remaining 6 bits as your TLB tag. So then when we want to look something up in the translation look-aside buffer, we first cut off this virtual page number, and then we can cut off 2 bits, check and see if there's an entry at that set number. So this would be set 3, because we've got 1, 1. And we check, well, is there a tag that matches this? So this is 3 again. Is there something in one of those 2 lines that has tag 3? And if there is, well, then what that can do is that can just give us back the correct physical page number right away. And we didn't have to go all the way down to main memory to the page table to look it up. We sort of bypassed the page table and just got it straight out of the look-aside buffer. Okay, so now we're sort of out of time, so I'm just going to skip through this quickly, but you can check the slides online if you want to see it in more detail. So sort of what we did, well, actually maybe Maybe I won't go through it quickly because I don't want you to see the answers if you want to go through it yourself. But what we do, we have the translation look-aside buffer, so we're going to do the same thing where we fill in the bits. But now we can check and see if it's in the buffer or not. And if it's in this buffer, then we can just give back the physical page number that we had before. If it's not, then we have to go all the way to the page table, which is in main memory. Any questions?